I'll do the introduction. So it's my pleasure to have Professor Sergey Koposov here today to give us a special CITA seminar. I think CITA is not running seminar in the summer, but it's great that Sergey is visiting, and we're very fortunate to have this talk from him. And I just started to introduce him. I wanted to say he actually spent past 90 hours on the airplane or airport, just let you all know that Lufthansa canceled one flight and delayed for 2 more flights for him to let him go from Shanghai back to Edinburgh. And they took a flight this morning from Edinburgh back to here. So I really appreciate that he's still agreed to give the talk today. I think he's still okay to give this talk. And the other thing I want to mention is that he refused me to call him Professor Koposov, because Professor in UK is special, that they have reader and a lecturer. They don't have a professor until you are a full professor. But I think I can call you professor now because you're recently promoted to full professor. So Sergey did his PhD, I think, at the University of Heidelberg, and then had a postdoc at Cambridge for several years before he became associate professor at Carnegie Mellon, and now he moved to Edinburgh as a reader and now a full professor there. And he has been, I would say, expert in galactic archaeology, near-field cosmology. He discovered many dwarf galaxies, many star clusters, and some stellar streams, and also some stars, interesting stars. And I think another thing I want to highlight is he probably built one of the largest person, single man built database, which is called the whole sky database that he used a lot of to do the science. And the whole Cambridge group used that for doing a lot of exciting science that you may have already heard related to Gaia and not related to Gaia. So today we're very fortunate to have Sergey here, and he's going to talk about the galactic potential and accretion history study using stellar streams. So let's welcome Sergey.
Thank you very much for the introduction, Ting. It's my pleasure to be here. And so today I'll be talking about the stellar streams and what they can tell us about the accretion history and the potential of the Milky Way. So I'll just start with a little bit brief introduction. So we obviously all know that we live in the lambda CDM universe, and one of the key predictions from the lambda CDM is basically this concept of hierarchical structure formation, that basically we know that all the large structures must have been formed from the merger of the smaller systems. And so, for example, based on this picture, if you would look in the dark matter distribution around Milky Way-like galaxy, you basically would expect it to be surrounded by a vast amount of smaller dark matter subhalos with basically this rising power law-like mass function. And so basically the Milky Way should be surrounded by tens and thousands of smaller dark matter halos. And initially, this prediction for this vast amount of substructure around Milky Way-like galaxies, substructure in dark matter, was not confirmed by observations, but actually in the last 20 years or so, thanks for the large amount of data coming from various digital sky surveys, we actually confirmed that the Milky Way is surrounded indeed by a lot of substructures. So basically, in the last 20 years, we've found tens of dwarf galaxies, satellites of the Milky Way. So here's a kind of reasonably famous plot showing the number of known Milky Way dwarf galaxies or satellites as a function of time. And so before we had just maybe a handful of dwarf galaxies known, and in the last 20 years, thanks to digital sky surveys, we now have many tens. So basically supporting these predictions of simulations saying that the Milky Way should be surrounded by a lot of substructure. And one thing that's worth also telling that if we look at the properties of those newly discovered dwarf galaxies around the Milky Way, they are particularly special. If we look at them in the space of luminosity of the galaxy versus size of the galaxy, basically many of these newly discovered dwarf galaxies around the Milky Way tend to be extremely faint, so they have luminosities all the way down to MV of 0, and they have large sizes, so corresponding to extremely low surface brightness of down to maybe 34 magnitude per square second. But so this aspect of the predictions of the lambda CDM was confirmed, but another aspect of the another consequence of this hierarchical galaxy formation is that Milky Way should also be surrounded not only by kind of intact substructures, intact subhalos or dwarf galaxies, but also the Milky Way should be surrounded by the debris from disrupted dwarfs and global clusters. And in fact, if we look at the numerical simulations at the halos of Milky Way-like galaxies, we see that basically you see that the halos are filled with this kind of linear features, which are basically debris from this disrupted dwarf galaxy. And the simulations predict that the Milky Way should be surrounded by a large number of this debris. And so basically my focus, the focus of my talk today will be this, the stellar streams that are produced by disrupted clusters and dwarf galaxies. Just a few words about this type of debris, the stellar streams, for people who maybe are not an expert on this. Just what is a stellar stream? So basically, the idea of the stellar stream is pretty simple. If you have like a stellar system that orbits a larger galaxy, and this stellar system starts to lose mass, lose stars, basically the stars are going to escape from two Lagrange points, from the inner Lagrange point and outer Lagrange points, and the stars lost from the inner Lagrange point is going to move a bit faster on the orbit, and the stars from the outer Lagrange point are going to move slower, and basically you're going to have this kind of one-dimensional tube of stars forming that's going to start to wrap around the galaxy. And another important point is that this type of stream would typically, roughly speaking, will follow the orbit of the original object, and that's going to be important later. So, so we know that the simulations predict that Milky Way should be surrounded by this streams from disrupted dwarf galaxies and global clusters. And again, initially we didn't really have that many known streams around the Milky Way, but thanks for the large surveys that were happening in the last 20 years, we actually found a large number of those streams. So first they were found using just photometric data. So if you just basically make the density of stars in the sky, you can actually find some streams. You can see them as a linear over densities, like here, from many papers. But in the last few years, we've also been finding many of these streams, not just photometrically, but using the data from surveys like Gaia. And this has been done, a lot of the work by the Stream Finders Corporation, by BATA and collaborators. So here's a plot from their figure showing many nearby streams found using basically phase space data. So basically, as a result of this work, by now, the number of known stellar streams is of the order of 100, and this is I think quite now a famous plot from Matteo and collaborators showing the known stellar streams, or at least the claimed stellar streams around the Milky Way, and you have you can see the different tracks on the sky, and yeah, the total number is probably around 100. And so one thing that I want to start with is just look at the population of the stellar streams and compare it to the population of the intact non-disrupted dwarf galaxies and global clusters. And I want to compare just the numbers. So right now we have about 100 stellar streams, but then let's count how many intact dwarf galaxies and global clusters we have around the Milky Way. And the number of dwarf galaxies we have around the Milky Way is around about 60 or so. Now maybe it's at 80 or something. If we look at the number of global clusters, the total number of global clusters around the Milky Way is probably around 150, but if we only count the global clusters that have been accreted, the number is probably about 60. So what I'm trying to get to is that if we now sum up the number of accreted global clusters and number of dwarf galaxies, we get a number that is very similar to the number of known stellar streams. So therefore, the stellar streams represent basically, in terms of number, easily 50% of the accreted systems onto the Milky Way. So this is a really important part of the Milky Way accretion history. And so therefore, we cannot just focus on intact systems if you want to understand the Milky Way accretion. So, but the important thing is also, yeah. Yeah, so this is like cumulative number of known dwarf galaxies as a function of time. And so now we have about 60 known.
So the global cluster, are you saying the dwarf galaxy descendant or something? That's not this distribution.
No, so yeah, so this is meta-institute, this is just...
I understand, right, but why are you counting the numbers?
Because, so what I'm trying to get to is the total number of the intact global clusters and intact dwarf galaxies is very similar to number of known stellar streams.
I didn't know they were the same thing.
No, it isn't the
No.
same thing he's saying.
basics
But the sources, I guess, of these streams can be global.
The sources of stellar streams can be either globular clusters or dwarf galaxies.
Oh,
And so therefore, basically what I'm saying is that the total number of intact systems is comparable to number of disrupted stellar systems. All right, and so now it's also worth looking at we know that the numbers are similar, or the number of disrupted systems and the intact systems are similar. Are they different in some other property? And so one way to look at this is to look at the accretion time of systems, the systems that are intact and orbiting the Milky Way, and the accretion time of the system that exists as streams. And so you can do that in numerical simulations. This has been done by Nora Ship and collaborators. And here I show, here they show basically the distribution of accretion time for the intact satellites. This is a look back at the accretion time, showing that for the intact satellites, they're mostly probing basically the last 6 gigayears or so. So basically the system that were accreted since Redshift 1 to now. However, if we focus on, say, stellar streams, this are shown here in blue, they are probing the accretion times that are much earlier. So basically, accretion time maybe before Redshift 1. So therefore, although in numbers, the streams and the intact satellites are similar, the streams are probing systems that are accreted much earlier. So therefore, we really want to study the streams if we want to get a full understanding of particularly early accretion history of the Milky Way. And so this is really kind of one part of the motivation for my talk to study streams. They really offer us an important picture of the accretion history on the Milky Way. So,
can you explain how long they're identifiable? In other words, if half the systems are destroyed, but how long do they remain identifiable?
So here, I know there's also, so at some point they stop being identifiable as streams, they start to be like phase mixed. And so I think it's an interesting question, like during what time you can see it as a stream and see its return progenitor, but I'm kind of not going to go into that. But in principle, in this study, they actually looked at which streams can be found in a way that's similar to observation. I'm actually going to show a slide where we compare the number of known streams versus what we can identify in the simulations similar to the data. So this is kind of the motivation for studying the streams from a point of view of accretion history. Another big part of the motivation for my talk will be using streams as probing of the potential of the Milky Way. And here, again, the idea is really simple. I'm going to follow up on that later on. Basically, the idea is that all those stellar streams, they approximately trace an orbit or in the potential. So therefore, if you know the positions and velocities of stars along the orbit, basically you can constrain the trajectory, and therefore you can constrain accelerations, and therefore you constrain the mass distribution. So that's basically the second motivation to study the streams in detail. And in particular, what I'm going to argue is that we need to study the streams spectroscopically, because most of the ways people have been identifying streams, they've been using either photometry or Gaia promotion. And so to really understand, say, the origin of the stellar streams, or to really measure orbits, we need, say, radial velocities of stars, or we need chemistry of stars. And so basically we need to get spectra for a large number of stars in these stellar streams. And so this has been the motivation for the survey that Ting here started, and that's been going on for the last few years. The goal was really to do the spectroscopic follow-up of a large number of streams accessible from the south, and basically get the velocities and chemistry using the 2DF spectrograph, which is on Anglo-Australian telescope, There is one important part that actually makes this survey possible, and this is the fact that we now have the data from the Gaia satellite, because I mentioned earlier that many of these dwarf galaxies that were found in recent 20 years, they are extremely low surface brightness. And the same can be said about the stellar streams. So when we look at the stellar stream like here, it has extremely low surface brightness. So maybe you can have like a handful of stars per square degree. So before, when people tried to do the spectroscopic follow-up of the structures, they basically were completely swamped by contamination. So to get like a handful of stars, a spectroscopy of a handful of stars, you had to follow up on thousands. However, with now data from the Gaia satellite, you can very efficiently filter out stream members, and so you basically can now actually sufficiently efficiently follow up basically the streams and get large number of stream members. And that's what we've been doing within S5. So this is just we collected about the spectra of about 100,000 stars in total, and this is some of the pointings that we got in the survey. We've been getting the velocities, we've been getting abundances, and in total we got probably by now about 20 stellar streams or so in the southern sky. And so a lot of the stuff that I'm going to show will be based on the data from S5. And so the first set of questions that I will try to answer in the kind of first part of my talk will be kind of general population questions. When we look at the streams, what are the progenitors of these streams? Are they dwarf galaxies or are they globular clusters? Also the question of chemical compositions. What's the chemical composition of the streams, and is it different from the chemistry of the attacked satellites? And also the questions of orbital properties of stars in the streams. So first, thinking about how can we separate streams that come from dwarf galaxies versus streams that come from globular clusters. And so here it turns out that one of the best ways of doing this particular analysis is look at the chemistry and specifically use the fact that when we look at the dwarf galaxies, it turns out that they typically show the spread in iron abundances because they basically have a multiple generation or kind of long enough star formation that basically you get the spread in iron abundances. While in globular clusters, you basically tend to have no spread in iron abundance. So therefore, you can use that as an indicator whether the system was a dwarf galaxy or globular cluster. And so here's a plot from one of these 5 papers by Ting, where each point is one individual stream, and so the y-axis here is a spread in iron abundance, and an x-axis is the average iron abundance, and you can see here there is basically a set of points where we have upper limits on the metallicity spread, and those basically can be attributed to globular cluster streams. And there is about 6 objects or so where we measure significant iron abundance spread. In this case, we can attribute those streams to dwarf galaxies. So one other thing that I also can say about this plot is for systems where we can say the origin is a dwarf galaxy, we can also map the metallicity into the luminosity of the system because we have a mass metallicity relationship, so we can correlate the average metallicity of the system to its kind of brightness or total stellar mass. And when we do that for this dwarf galaxy streams, we basically get luminosities of about -6, -8. So it's basically this kind of intermediate regime between the so-called classical dwarf galaxies and ultra-faint dwarf galaxies. And the most likely reason why many streams sit here and not, for example, here is because the streams coming from fainter dwarf galaxies just would be invisible right now. So this is, to some degree, a result of selection effect. So it turns out that one can try to separate dwarf galaxies from streams from globular cluster streams using other methods, maybe use the velocity dispersion, but actually this method doesn't quite work because it turns out that you can actually increase the velocity dispersion in the stream through kind of dynamical means. So therefore, it's not a great separator between the dwarf galaxy and globular cluster streams. You can also use just the width of the stream and try to use that to separate globular clusters from dwarf galaxy streams. So here's just one plot showing the luminosity of the system versus size, and the points here are globular clusters or dwarf galaxies, and on top of that, the triangles show the streams coming from globular clusters in red and streams coming from dwarf galaxies. And here you can see, roughly speaking, you see that dwarf galaxy streams are a bit broader than global cluster streams. But this is not a perfect separation. The chemical way is really the best way we know so far to separate one type of stream from another. So since I started talking about abundances, in fact, right now, I think we started to assemble quite a lot of data on individual element abundances in some of the streams. So, for example, in this work by Alex G. and the collaborators, we actually looked at the individual large number of abundances of different elements in this population of stellar streams in S5. So here is the various elements like magnesium over iron versus iron, and here each stream is shown by field point, while the dwarf galaxies are shown by empty points, and the Milky Way shown as a gray band. Here, the basic conclusion from this is, first, there is so far there is not that much data on the streams, but basically it seems that there is no clear difference in chemistry that we can notice between the dwarf galaxy streams and the intact dwarf galaxy. So they seem to be chemically similar. This is as far as you can see. But the same cannot be said about the streams that come from globular clusters. In fact, over the last few years, there have been several discoveries of the streams, globular cluster streams, that were found to be particularly metal poor. So, for example, in this paper by Wang and collaborators, they found that the one particular globular cluster stream had metallicity of -2.7, and then there are a few other streams claimed recently by Nicolas Martin and collaborators claimed to have metallicity of below -2.7. The reason why it's interesting, because previously we thought that there are no globular clusters below that limit. So basically, so far, the most metal poor global cluster stars, we know they are in streams. And I know this is kind of supported by also this plot. This is from a recent paper by Ibata, showing the distribution of metallicities for the streams versus distribution of metallicities for global clusters. And there seems to be a bias, metallicity bias for the streams versus global clusters. And so I think it's not quite clear what's the exact reason for this kind of difference. But the most likely explanation from my point of view is that basically we know that the streams are associated from systems that were accreted earlier. So therefore, it's so surprising that the global clusters in those systems are different from the ones that are accreted later. And so that possibly explains the metallicity difference here.
So it's between galactic system and clusters that outward make the metallicity.
So in the Milky Way, so the inner global cluster is kind of the in situ. They're formed within the Milky Way.
So there aren't be more metal or other, but there's also less dense.
Sorry?
Isn't there a trend of density and metallicity in global cluster systems? Reaching back decades into my computer astronomical knowledge.
I'm not entirely, I don't know. I don't know if there's a correlation of density and metallicity.
I think that they would be less dense.
I think just because less dense ones will not survive in the center. Yes, just due to survival reasons. So I'm not.
I mean, obviously, you can look for a parallel trend of existing systems to see it.
Yeah. All right. So I think this question was already mentioned. So we can obviously, so we have now a sufficient statistic of the streams we see in the data. We can also look at we can compare the streams to numerical simulations. And so this is again from the work done by Nora Ship, for example. So here is the cumulative. So here in black, this is shown for the data, the cumulative number of streams above certain mass. And in blue here, this is shown in the simulation. And at first, there seemed to be kind of big discrepancy in terms of numbers. But it turns out that basically, if you take into account the which streams in numerical simulation can be detected using whatever method we use in our data, then actually this disagreement mostly disappears. So in that sense, there seemed to be no mismatch between the number of streams in the simulation and the data. However, I want to say that this comparison was done for dwarf galaxy streams, because the dwarf kind of simulating globular cluster streams is kind of harder, because forming globular clusters is difficult in the simulation, and disrupting them is more difficult as well. Okay, so just another point, talking about this population of the stellar streams in the Milky Way. It's also now become possible to actually look at the global orbital properties of the stellar streams, because we now have basically full 6D information for many of those stellar streams. And in S5, for example, we have done those measurements. And so, one way to kind of look at this this population is, for example, look at the, say, for example, energy angular momentum space here, where here basically the ellipses correspond to different stellar streams, and the dashed lines show the different globular clusters or dwarf galaxies. And so now we can start to, for example, try to associate maybe different streams to like one big accretion event, where maybe several global clusters were accreted together, or we can start to kind of associate streams to dwarf galaxies or global clusters. Unfortunately, it's kind of actually becomes quite difficult, because right now we have those 100 stellar streams, we have more than 100 global clusters and dwarf galaxies, so this space actually becomes quite crowded. So this associations becomes quite tricky. But it's still possible to, for example, look at the kind of broad statistical properties of the orbits of the streams. So, for example, here what is shown is basically the kind of distribution of the orientation of orbital planes of the streams, such that basically here we have a prograde rotation exactly aligned with a Milky Way disk, and here we would have a retrograde kind of aligned with the disk. And here we have polar orbits. And here in green, shown is the distribution of the streams in S5, observed in S5 project. And what you can see here is, in S5, there seems to be some bias of streams towards prograde rotation. But this is a reasonably small number statistic, and I think it's probably too early to say whether this is a kind of physical effect or just maybe either a small number statistic or some kind of bias of our sample. So kind of just maybe concluding the first part of my talk, just I want to say that I think it's clear that the population of streams in the Milky Way is basically comparable to the total number. The number of streams is comparable to number of intact satellites, global clusters, or galaxies. And this population, the population of streams, are probably much earlier accretion events. And we start to see that in terms of properties, for example, in Metallistes, this population is different from the population of intact satellites. And so this is kind of the first part of my talk. So the next part of my talk, I want to focus on what the streams can actually tell us about the nuclear potential. And here again, basically, I mentioned already this idea that the streams trace the orbits and therefore probe the potential. So
before you go on,
yeah.
just looking at your conclusion, back to your conclusion slide, first part. Are the intact bodies more prograde than retrograde, or is there any kind of preference?
So here I should show. So there are faint dwarf galaxies, which so with the luminosity is below -6, which seem to show similar kind of bias.
They also
Yeah. So, but I know this is like kind of selected subset for only faint systems. So maybe it's kind of connected to some kind of group accretion that's like kind of produces this bias.
It's not because, say, the prograde system somehow is more subject to tidal disruption.
I know. I think there could be survival-related kind of effects, but I cannot say how important it could be. Okay. Right. So now coming to this streams as probable potential, and so I know people been trying to use the streams as probable potential for quite a while, but I think there was definitely a lot of kind of enthusiasm in this field, particularly like in maybe about 10, 15 years ago, when in SDSS been a lot of there've been many thin stellar streams found like for example, this GD1 stream, which is this is density of stars in the sky. This stream is like 60 degrees long, and I had at the time a paper where we measured the flattening of the potential of the Milky Way using this thin stream. This is contours on like flattening and circular velocity, and then actually Joe had a paper on where he used the data on this stream and the Palomar 5 together, and also providing very thin kind of tight constraints on the galactic potential parameters. And for a long time, it seemed that we just need to collect data on more streams, and we'll be able to make really tight constraints on the galactic potential. So, for example, there was this kind of really nice study by Anna Bonazza in 2018, where she kind of simulated multiple stellar streams in the Milky Way and tried to imagine what would be our uncertainty on the flattening of the potential as we get more and more streams. And the key point there was that not only the uncertainty unsurprisingly goes down as we get more streams, but the uncertainty decreases actually faster than like 1 over square root n, because not only new stream gives you more information, but also the new stream breaks some of the degeneracies, because streams probe different like orientations and probe different radii. So it really kind of based on these studies, it seemed that we just need a large number of streams and we'll be able to get really accurate constraint on the galactic potential. However, I would say kind of a significant problem of this approach was revealed when the early data from the Gaia satellite started to appear. And this is, I think, probably quite famous plot from a study by Bryce Willen and Anna Bonazza, so showing one of the stellar streams that was used in previous studies mapped in Gaia. And basically what you see is that the stream itself doesn't look like just one nice, like a kind of Gaussian tube around the orbit of the progenitor. Instead, you see the stream which shows some kind of gaps in the stream trajectory. You see some stars that are kind of misplaced with respect to stream track. You see some areas where the stream is maybe much broader. And so this really doesn't look like just again, nice stars just that basically follow more or less an orbit. So what could be the cause of that appearance? And so one of the key reasons why the stream may appear like that is because we know that streams are very sensitive, especially the thin streams are very sensitive to small perturbations. So if you have a stream, for example, you have something fly by, next to it, some perturber, basically what will happen to the stream is you create some kind of wave, basically, in the stream, and if you let it evolve over time, basically the wave will kind of propagate, and what you get in this result is a stream with a gap in the middle, and also some stars that are more spread out around the stream track. And so, in particular, this effect is expected to happen due to, for example, dark matter subhalos in the Milky Way. And as a result of that, basically, if we look at the what would be expected, I don't know how this would work in Zoom. Okay, so basically, if we look at the numerical simulation of these streams in the realistic dark matter halo, basically, you would expect that the streams over time would encounter more and more dark matter halos, and basically that would make the stream kind of much more disturbed and more messed up, as opposed to this kind of ideal picture of a kind of nice Gaussian tube of stars around the orbit. Unfortunately, this is a bit choppy over Zoom. But then the main point here, you can see already that the streams definitely are more kind of perturbed, kind of messed up by this interaction with dark matter halos in this case. And so the question is this really what's happening to the real streams we observe? Is this really a result of that? Those sorts of interactions. And so one way we can understand this is we look at more streams. And so, for example, one stream that we've looked at some time ago is the Palomar 5 stream. This is this stream here, and what we've done, in 2017 is try to look at the stream here and basically extract the density of stars along that stream. And this is shown right here, with the density along the stream. And basically, if you look at the density, there are two regions where the density seems to be decreasing. Here, basically, goes down by roughly a factor of 2, and here is also kind of somewhat decreased. And this is not something that you would naturally get from just standard disruption of the global clusters. And so the question is, what can be the cause of that? That's certainly not the only explanation, but one can try to explain these features in terms of the perturbations. We did this in this paper. So here is the result of assuming that this stream was hit by two perturbers. One is 10 to the 6 solar masses, the other one is 10 to the 8 solar masses. And so here is our data in blue, and in black, this is a numerical simulation where it was hit by two subhalos. In this case, the model matches the data. But there are plenty of other alternative explanations. For example, where the perturbers doesn't have to be subhalos, where they could be, say, giant molecular clouds. So this is just one more example of the stream. It shows kind of features that are not necessarily expected from just standard global cluster disruption. There are many more cases. So this is the case of the stream. This is this so-called Atlas stream, and this was previously thought to be a different stream called Dalika-Uma. And when within S5 we've been getting large number of spectra in this system, we basically have seen that these two streams that were considered to be different, in fact, the radial velocity of this part basically followed the same trend. So this is basically the velocity of this structure is kind of the same. So basically, this is not two different streams, but in fact, this is not two different streams. This is just one single stream, which for some reason show this particular kind of gap or displacement in the middle. And this is about 500 parsec. So this is quite large. And so again, it's not quite clear what could have caused this. In recent paper by Hilmi and collaborators, we tried to again model this stream, assuming it is caused by some kind of perturbation. So here we basically collected all the data on the stream track, on proper motions and radial velocity, and then we basically tried to model what kind of perturber you need. In this case, this is a kind of contours in blue for the perturber mass and perturber size based on the current data. And so currently, the error bars are reasonably big, but obviously if we get the future kind of more accurate radial velocities, we may be able to constrain the parameters of the perturber better. And in particular, what will be interesting to do in the future is if we can actually then not only just get the estimate of the mass of the perturber, but maybe say where it is right now, and because then we can actually go and look at this location. Is the actual global cluster of dwarf galaxy at this location? And if there's nothing visible, that would probably support the idea that the perturber is dark. In this case, it may be a dark matter subhalo. So basically, kind of summarizing this part, what I want to say is that basically most streams that we looked so far, they really seem complex and they show vast range of features and structures. So I already showed this picture and this picture here. This is just another stream which shows basically kind of two parallel kind of sequences. And I would say to a large degree, we cannot really fully understand what is the cause of this complexity. I think there are a lot of explanations and they are all very sensible, but in most cases, we don't know what exactly caused this perturbation. And kind of summarizing this part here, what I want to say is that unfortunately, this complexity of every stream we see is a kind of major factor that prevents us from using all these streams to constrain the galactic potential. Because, if your model cannot reproduce all the features of the stream, can you really trust that this inference of the global potential parameters of the potential if you don't know what caused this stream gaps or the stream kind of wiggles? So I think this is a kind of major problem if you want to constrain the galactic potential. However, this problem comes at the potentially big potential of important results if we can indeed confirm that some of these features are caused by dark matter subhalos, because then we can really constrain how much kind of many small dark matter subhalos there are, and we can constrain the dark matter model. So although this kind of part of my talk was quite negative in the sense of that, I think in my opinion, it's really hard to use streams as a probability potential because of the substructure. In the kind of third part of my talk, I'll talk about one case where we can actually use the data to get quite accurate parameter constraints on the nuclear potential. This is the case of one particular stream, the stream called Orphan, which then discovered quite long ago, basically about 20 years ago. This is one of the discovery images. You can see it here on the sky. And this stream was discovered a long time ago, but when the Gaia data came about, it was possible to trace it basically around pretty much the whole galaxy. So here's the just XYZ projection of the stream. So here are individual stars, are individual aurora in this particular stream, and the stream is basically about more than 100 kiloparsec long and more than 200 degrees on the sky. And so when in 2019 when we started to kind of look at the stream in 3D, it already became clear that something is a little bit kind of strange with the kind of shape of this particular stream. So here is just in 3D, the black is the galactic center, and in blue are the stars belonging to the stream. And from here you already see that it doesn't seem that the galactic center lies in the kind of in the plane formed by the stream, which is a little bit weird. And then if you look at the stream on the sky, this is basically the stream here. It looks like it's a little bit twisted, and at the time that seemed a little bit surprising. And so we started to look further to this as well.
I'm sorry. I was trying to turn this back. My sincere apologies. We were meeting earlier in here, and
Sorry for people online, we're gonna, I hope the Zoom is,
I'm assuming the online people can see, but
can someone who knows about this kind of stuff check?
is it on or
It's the same brand, so the remotes are. Yeah, it's on.
okay. It is two controllers.
It's two controller, but the projectors have the same brand, so they
all right. So basically we saw this kind of little bit weird spatial distribution, but then we started to look at the motion of stars, and so here is the basically individual stream stars, and the arrows show the direction of motion of stars. And what we saw is that in one part of the stream, basically the stream stars are moving along the stream, while in another part the stream stars are basically moving at an angle. And then that's not something you would expect in streams, because most streams are basically like a train on a railroad track, where all the carriages should mostly follow the railroad. And so the fact that basically we saw stars moving at an angle meant that basically the only way to explain it to some kind of external perturbation. And in this case, basically the only perturber capable of doing that is the Large Magnetic Cloud. And so basically from this, so this is in fact the kind of illustration of what was likely is happening. So here you can see the stream, and then you can see the kind of LMC passing by and basically perturbing the stream and forcing it to move sideways. And one of the kind of conclusion from this result was the understanding that LMC basically must be sufficiently massive, basically needs to be at least, I don't know, about 10% of the Milky Way mass to reproduce the observed effect. And this, in turn, the understanding that the LMC is so massive actually lead to another kind of sort of problems that makes the job of understanding the Milky Way potential harder, because the massive LMC introduces, for example, the kind of complicated response of the dark matter halo of the Milky Way to the LMC. So, for example, you expect due to dynamical friction, like a big dark matter wake following behind the LMC. Also, because when you have LMC, which is 1/10 of the mass of the Milky Way, you cannot assume that the Milky Way center is static anymore. You basically have to model that the Milky Way center orbits around the common center of mass. And basically you have a time-varying potential, which again is another complexity in this kind of quest of understanding the Milky Way potential. And so despite that, we still thought that this stream, the Orphan stream, that I talked about. I don't know, I got this. I don't know if I got disconnected. So basically, we still thought that it's this particular stream, because it's so long, more than 100 kiloparsec long, it's basically a great, could be a great tool to try to constrain the Milky Way potential and this interaction between LMC and Milky Way. So over the last 4 years or 5 years, within S5, we're basically obtaining a large spectroscopic sample of stars in this particular stellar stream, getting basically radial velocities, kind of getting probe motions from Gaia and so forth, trying to map the stream in detail. And so here's just one of the kind of summary plots from this. For example, this is the density on the sky from this stream, and this is a probe motion in the stream. And again, you can see the fact that the stars are moving at an angle with the stream, and you can see LMC here. So basically, this part of the stream is bent just because basically it's being pulled by the large magnetic cloud. And so, I know this is just a kind of illustration, but really the main goal was to try to model this stream and try to extract the parameters of the Milky Way potential and potential of the LMC. So we basically had a quite a sophisticated model of the stream disruption, where we had we let many parameters to be free, the parameters of the Milky Way potential, the LMC potential. We also were modeling things self-consistently in the sense that the motion of LMC was done in the actual in the potential of Milky Way. So and we're all moving around the common center of mass. And so here on the right, this is just an illustration of the kind of all the data we have for the track on the sky distance modulus, and then blue is the best fit model that was able to match the data pretty well. And one of the kind of key results from this was our ability to get accurately the mass profile of the Milky Way. So here is the cumulative mass profile of the Milky Way as a function of the distance from the galactic center. Here is in red, this is basically the posterior 1 sigma error bar. And here we show the fractional error. So in this range between about 20 and 60 kiloparsec, we achieve the fractional error of maybe 5%.
So is this model done via n-body or?
No, I think the OMC was modeled as a point mass, but it was assumed to have a dynamical friction using a Chandrasekhar prescription. So it was like
so you had some sort of like analytic prescription to try to account for complicated effects that you were showing.
Yeah. So it didn't have any deformation of dark matter, for example. So
so this wake that you were showing.
No, it didn't have this dark matter wake effect. I'm going to show one slide which there are some models that can try to do that, but those models are obviously so much harder to run, so you cannot actually do the fit is right now. So here was like basically analytic potential for the Milky Way and kind of analytic potential for the LMC moving around the common center of mass. So here we get the mass profile, and obviously one can get the total mass, but obviously that's always require extrapolation. But another kind of, I think, pretty interesting thing we get is we actually get the constraint on the mass profile of the large magnetic cloud. And importantly, we not just constrain the total mass of the LMC, because the stream actually approaches LMC at kind of range of distances. So the closest approach distance is about 20 kiloparsec. So this part, the potential, we actually directly probe with the stream. So our model actually is allowed to have truncation of dark matter of NFW. And in this case, we can basically claim that if dark matter halo is truncated, it's truncated further than 55 kiloparsec. So from that, one can, for example, get claim that there should be dark matter from the OMC, like in the solar neighborhood. So I think that's quite an interesting result. So the thing that's related to your previous question is that, so in our model, when we tried to fit the stream, we just had this kind of reasonably simple analytic prescription. But obviously, in the real world, we know that the dark matter, for example, is being deformed. What was shown in this paper by Sophia Lillingen in 2023 is that the data that we have at hand actually already sensitive to this detailed deformation. So in this case, they run some of those models and they kind of try to enable some deformation and disable some. And basically, we see that that produces differences in the stream tracks, for example, that we'll be able to distinguish. But at the moment, it's really hard to fit those kind of model like in the same way we did earlier. Just those are computationally much more difficult. So this is obviously one way, for example, where this stream can also tell us something about the nature of dark matter, because let's say if we consider some maybe self-interacting dark matter models, this maybe deformation would happen somewhat differently. So another thing that the stream actually can also tell us something about dark matter is through probing the dynamical friction, because it turns out that because the stream is very sensitive to where OMC is and was in the past, we can constrain the past OMC trajectory very well. So for example, we can plot the past OMC trajectory based on the current priors. This is a red set of curves. This is like in some YZ coordinates. And you can do the same thing after using our stream data. And basically you get quite shifted OMC trajectory. And the point here is that the trajectory of OMC is sensitive not just to the Milky Way potential, but also to the strength of dynamical friction. And right now, we start to be able to probe the strength of dynamical friction, which again is something that can potentially tell us about some of the dark matter properties, because in some dark matter models you get different degree of dynamical friction. So, kind of summarizing this part here, I think although I was previously kind of quite negative in our ability to use the streams to constrain the potential, I think in this case, this stream is actually able to deliver some strong constraints on the Milky Way potential and OMC potential, but we do have to include the OMC in this kind of modeling. And just maybe the last two slides I want to say, so far I've been mostly talking about the data that you can get from S5, but obviously now we live in this kind of era where there are many large ongoing spectroscopic surveys. And so one of the surveys that I've been actually involved in is the DESI survey, which is a large survey done by the instrument at Kitt Peak Observatory, which can simultaneously target 5,000 stars at the same time. And one of the things that this instrument has been doing is doing the Milky Way survey that's observing basically many of the streams that I talked earlier about. And there are some kind of papers that are written right now on those streams. Unfortunately, I cannot show you that yet. However, I can show you some brief slide on the result that was published last year, where we actually used this instrument to study the streams not in the Milky Way, but the streams in Andromeda, where basically it turns out that the field of view of the DESI instrument matches extremely well the Andromeda galaxy. And so just by placing a few fields, we can really probe well some of the substructures, some of the streams that we know in Andromeda. So we know that Andromeda has this large number of streams, and we have basically multiple fields that allowed us to probe this particular giant stellar stream. And the paper that was published last year by Arjun Day, John Majid, and myself and others, basically we used this data to, say, probe the parameters of the MT1 potential, the mass of the NFW, the dark matter halo, etc. But this is just one stream. In fact, what we've been recently doing is we got some additional data on some of the thin streams in Andromeda, and the goal there is to use this kind of data to basically the same kind of analysis that we're now able to do in Milky Way, start to be able to do in Andromeda as well. So hopefully we'll have kind of similar understanding of the Andromeda potential to the one we have in the Milky Way. And I'll stop here. A lot of time. Stop here. Thank you very much.
Okay, thanks very much. That's probably a lot of concerns here. Any questions? Any other questions? Any more?
There are a couple of, or many different explanations potentially for all these Accretion streams. Are there any additional observable differences that you would expect from, say, a dark matter simulation versus perturbation by a giant molecular cloud?
So, okay, for the giant molecular cloud, I think the easiest way to distinguish things is like prograde and retrograde orbits, because I think if you have a stream in the same direction as a disk rotation, you would expect a bigger signature. So I think that's I think the easiest way to separate. Obviously, if the stream is distant enough, also probably it cannot be giant molecular cloud. I think it's hard to separate say perturbations, say, from global clusters and faint dwarf galaxies and just dark matter subhalos, because it's essentially kind of the same thing. Yeah, so I think there are all these different scenarios produce potentially different features, but I don't think I've seen at least this kind of analysis that try to maybe classify all these features and kind of make statistical analysis what could cause what features. At least, I mean, in my view. It would be great if most of this is caused by dark matter subhalos, but I'm personally not sure of that.
Any other question? Yes.
Does the LMC have its own streams?
Most likely, yes. I'm not sure I'm aware. Okay, I think, I should have been on some papers that claim streams.
Constraining mass.
Yeah, so I think it would be great if we had the streams, but obviously LMC is also interacting with SMC. So if there were streams, they would be messed up in an additional sort of way. So I think most likely we'll find streams around LMC, but it won't be easy.
Any other question?
So are there any streams for which the progenitor has definitely been fully disrupted?
So most streams don't have a progenitor.
Oh, okay. So most streams you can exclude that there is a surviving remnant progenitor.
I'm not sure about exclude, but so most streams will look. I know within the observable kind of extent of the stream, there is no visible overdensity associated with global cluster of gaps. That for the majority of the streams.
Okay, yeah.
That's actually kind of, I think, an interesting problem in itself. I skipped the slide, but I had a slide on that because, and it's different. The interpretation of this is kind of different whether you're global cluster or dwarf galaxy, because the disruption of global clusters introduces this kind of sort of three-body interaction effects or whatnot. So some people claim that to reproduce the population of global cluster streams, you need, say, global clusters dominated by black holes, because that kind of the disruption of such global clusters goes a little bit differently to the ones that if you have a global cluster not dominated by black holes.
A large black hole.
No, like just the population of external mass black holes. Oh. There was a recent paper by Mark Hillis and collaborators trying to claim that. I don't have a strong opinion on that. But I think for for dwarf galaxy streams, I think at least my personal interpretation of large number of the fact that many streams don't have a progenitor is that the disruption happens in kind of almost like bimodal regime. Either the disruption is really slow, in this case the progenitor sticks around and we don't detect any stream at all, or the disruption is fast. In this case, basically the progenitor disrupts very quickly and we just see the stream. And it's really hard to be in the middle where the stream is bright enough and the progenitor lives long enough to be observable. So that's kind of my wavy interpretation, but I don't have study that to support that.
So 2 comments for these topics are using my post about. One thing is, like among all the streams that Sergey talked about today, I think only PAL5 is the one with the known progenitor. That's why it's called PAL5, because it's a known global cluster. All the other one was with some weird name that none of those has progenitor. The second thing, that's something I just learned while I was at KITP for this dark matter conference. If dark matter really make cusp halo for those ultra faints or for the faint end of the classical, my understanding is the cusp core will remain forever.
This is the origin of my question.
Yeah, that's basically your question. That's why I want to bring
Yeah,
this up. That's kind of what I think the question is from. So we expected the dark matter component of that core will survive forever.
The cusp.
For cusp, yeah. But it's stellar part, whether or not it can survive forever or not. I think nobody has really done that, and there's no simulation actually show that. It's a very interesting topic for people to run those simulations to see what is the survived cusp core. But some of those streams, I think, is in the regime of between cusp to core transition, based on the stellar feedback. So it's hard to say if any of those are actually formed in the cusp profile, on the cusp core profile. But my understanding is that even for the CDM people, they think that the core is cusp. The stellar component might still be completely destroyed. But we definitely have some dwarf galaxy stream here that has no progenitor seen. Either we haven't seen them, or they're just too faint to be able to see. Any other question for Sergey? We are at the hour. Okay, let's thank Sergey again for a very nice talk. For the next 2 weeks and next week, and so tomorrow he will be here using the director office. For people around in CITA, you're welcome to drop by and talk to him, sign up on the spreadsheet, and he can find you in the office. For the rest of the 2 weeks, he will be at the AB building at 2 to 6. You guys are welcome to stop by anytime. And also please invite him to any events that you are aware of that is maybe related to galaxy archaeology or music cosmology. Okay, thanks all for coming. And for people online, we are ending talk today. Thanks. Oh, I didn't check this question. Oh, I'm so sorry. No, it's okay. And I don't see a chat. Okay,
Do we have local guys?
we could. I got that you have your.
So, that's like two.
I want
so-
you should know. I was thinking for next week, so guys, we have to talk about it.
Yeah.